Welcome to this chapter 4, linear regression with one regressor. In this chapter, what we are going to discuss: population regression function, sample regression function, how to estimate population regression function, what is ordinary least square, what does this least square means, why should we not have outliers in our data, and if there are outliers, why OLS lead to biased results, sampling distribution of OLS estimators. These are main issues which we are going to discuss. This is our first chapter in a course on Introduction to Econometrics from Stock and Watson. I hope you are all familiar with probability and basic statistical inference. I am not going to cover it at the moment in this course. So this is my first lecture on Introduction to Econometrics, linear regression with one regressor. So, and our fundamental question, basic question is, does class size reduction lead to improvement in test score? We'll discuss California school data used in this book, Introduction to Econometrics by Stock and Watson. What is estimation? What is hypothesis testing? How do we do confidence interval? These things we'll discuss in this chapter as well as in chapter 5. Next we'll discuss in chapter 6, multiple linear regression. So if you want to get more on concept of OLS estimators, you can watch this video, that what do we mean by OLS, ordinary least square. How does it make sum of squares of residuals minimum? We'll discuss it at some other stage. So what is our population regression function? Our population regression function is simply that test score is equal to beta naught plus student teacher ratio class size. What is beta 1? We'll focus on beta 1 slope coefficient. We'll not focus on beta naught in this chapter, and will not focus on beta naught a lot in this cross-sectional data. So slope is basically rise over run, how much increase in test score will happen due to an increase or decrease in sample size. So this rise, how much rise for this much run, that is your slope. This is measured by beta 1. If it is negative, it will be like this. So beta 1 basically measures impact of class size on test score. We don't know beta 1. We need to estimate this beta 1. And we know that there are many other factors which influence this YI test score. So those factors effect is in UI. So X is called regressor, predictor, explanatory variable, independent variable. Y is called dependent variable, predictand, regressand, response variable, outcome variable. So there are so many names to these variables. Beta naught is called intercept. What's its interpretation? Why should we avoid its interpreting the way we do it in mathematics? What is slope? Beta 1 is your slope and UI are your errors. What is difference between errors and residuals? That we'll also discuss. There is a difference in residuals and errors. So you see, this is our average regression line. This is our average regression line, and difference from this average regression line and actual Y, these black dots are your observed Y values. This difference is called residual, which is our error at the moment. From errors are some hypothetical thing, we'll discuss it. These are called errors. So difference between the average value you have guessed and the observed value. So this is your Y hat, this is your Y. So the difference between these two is called error. We try to fit this line in such a way, this blue line in such a way, that sum of squares of errors is minimized. Since errors are unobserved, we always get from sample the sample errors you may call residuals. So we say sum of squares of residuals. As we minimize sum of squares from mean, similarly in ordinary least square, we try to make this square as least, or this is called least square. So we try to pick those values of beta 1 and beta naught and beta 1 which makes this sum of squares of residuals minimum, sum of squares of errors minimum. That is what has been discussed in slide number 3, concept of OLS. You can watch that video. I'll give the link in my this video as well. So this is a scatter plot between test score and student teacher ratio. In general, what we observe from this scatter plot or from this exploratory analysis, that there seems some sort of negative relationship between student teacher ratio and test score. That is, as class size increase, that is on horizontal axis, test score decrease. So it seems a line like this one. So should it be this one? Should it be this one? Or it should be this one? So which line to fit? The one which makes, or where beta naught and beta 1 are chosen such that sum of squares of errors residuals is minimized. That is, those are called OLS estimators, because those estimators basically make this difference between residuals and fitted values their minimum. So this is ordinary least square basically tries to pick beta naught and beta 1 in such a way that this sum of squares of residual is minimized. You can do its calculation, that differentiate it with respect to beta naught, with respect to beta 1, this square differentiate with respect to beta naught equal to 0, differentiate it with respect to beta 1 equal to 0, then second order condition should be, the second differential should be less than 0. That's mathematics which you have, might have already done. Here I am going to discuss in more you see applied sense. So beta 1 hat is equal to sum of xi minus x bar yi minus y bar divided by sum of xi minus x bar square. If I divide it by respective n minus 1 n, this is called, the upper term is called covariances, and these will become variances. So if we divide it by n minus 1, these will be called covariances. So beta 1 hat is covariance between x and y divided by variance of x, or if you simplify it, it may be written, it was written earlier. Beta naught hat is equal to y bar minus beta 1 hat x bar. Our fitted line, which is, you see, we don't have data on population. So we have to get data from sample, and when we try to get data on sample and fit a line on sample data, that's called, know your residue, these are called residuals. Errors is some sort of conceptual thing that's in back of your head, that's not available. Errors always satisfy all the standard properties. Issue is always with residuals. So residuals is equal to yi minus yi hat. Beta naught hat and beta 1 hat are those values which makes sum of squares of residuals minimum. So you can see that if you pick any two values other than 698.9 and minus 2.28, your sum of squares of residuals will be more than what you get by picking these two values. This is called ordinary least square. Here what do we say? That beta 1 slope coefficient is minus 2.28, that as class size increase by 1, test score decrease by minus 2.28, or as class size decrease by 1, that is test score will improve by 2.28, minus into minus plus. So here you see, we see what is the interpretation of slope. But what will be average test score when class size is 0? What do we say? 698. Mathematically it's okay, but do we have ever observed class size of 0? Since we haven't observed class size 0, so we should not make any statement about test score for 0 class size, because we have never ever observed this data. So we should not make any statement about predictand where we don't have predictor. Weight is function of height, but have we ever observed height equal to 0? So we don't have any person, anything with height equal to 0, so we should not predict where we don't have predictor. That's why we say that avoid interpreting intercept. And that is my video, interpretation of the intercept. You can watch this video from this playlist, Econometrics, a practical approach, interpreting the intercept. These are short clips. Here I am trying to make comprehensive ones. So that's what we have discussed. Here what do we see? That if class size is 19 point something, what will be your guess? What will be your what will be your estimated value of test score? What do we get from mathematical, from simple algebraic calculation? 654. What will be your the actual value? That will be 657.8. The difference between this one and this one is called residuals. Why we fit always average value? Because if I ask you, okay, let's play a game that I'll pay you $50 if your guess is within 1 point, minus 1 point or plus 1 point lower than actual value. Now you see, let's say we are given a value of 20. If you guess this one and actual value is this one, you will miss by a huge margin and you have to pay a good amount of money to me. And if you guess this one and actual value is this one, again the same. But whenever I give you class size 20, and if you guess on this test line, so you will be close to these points than by guessing some individual value. So what do we see? We always average these vertical values against a given x values. So when we average, its average is here, its average is here, its average. So we pass a line through these averages. This is called average regression line, or this is called regression line. So whenever you are given data, if you don't know any particular criteria for guessing, average will be your best guess and regression is average line. If we run through Stata, I'll do it through R. I have already uploaded and given the link for running all this in R Studio, and I have given all the codes so you can use those codes. And in Stata, I have a video that how you can do this. What is the meaning of this robust? That I will explain in my next video on chapter 5, heteroscedastic robust standard errors. So you can run these codes. Until and unless you run it, you make scatter plot, you will not enjoy. Measure of fit. So we are going to discuss some terminology here. R square. What is R square? This is fraction of variance of y that is explained by x. It is a unitless measure. It's between 0 and 1 so long as intercept is included. So R square is basically how much variation in y is explained by x. Smaller the variation, it means we cannot predict better the dependent variable. But more than that, saying anything more than that about R square, that's be careful. We'll explain it in chapter 6. multiple linear regression, that high R square, low R square, that doesn't mean much for us in having analysis when we are studying behavioral relationship, structural relationship among the variables. Standard error of the regression measures the spread around the regression line. That was your regression line, these points, that spread around regression line is measured by standard error, or you can say it is roughly equal to the size of a residual. So yi is equal to, we decompose observed value into two parts. Yi is equal to your explained fitted systematic part plus random part. And when we take its mean, y bar, y hat bar, u hat bar, and we do subtraction and little mathematics, we'll have total sum of squares, explained sum of squares, residual sum of squares. So that is what we have done, sum of yi minus y bar square. Similarly, yi hat minus yi hat bar square. Similarly, plus sum of ui hat minus u hat bar. So u hat bar is always 0. So ui hat square. So this one is residual sum of squares. This is explained. This is total sum of squares. And r square is equal to explained sum of squares divided by total sum of squares. Since total sum of squares is equal to explained sum of squares plus residual sum of squares. So residual sum of squares will be equal to total sum of squares minus explained sum of squares. So this can also be written as 1 minus residual sum of squares divided by total sum of squares. R square is 0 if there is no variation in y due to x. R square is 1 if there is complete variation explained in y due to x. Usually R square is between 0 and 1. For regression with a single regressor, R square, the square of the correlation. If you have only two variables, then R, X, Y and its square is the same as R square. But it's not true if you have more than two variables. Standard error of regression is ui minus u hat bar. U hat bar is always 0. So sum of ui hat square divided by n minus 2. Root mean square error. So this is square sum of squares error. This is when you take its mean. This is mean square error, and then you take its root. This is root mean square error. Difference between root mean square error and standard error is degree of freedom. So if n is small, n minus 1 over n minus 2 and 1 over n will be different. But if n is very large, then there will not be much difference. So standard error of regression and root mean square error will be very close to each other. As I mentioned, the standard, okay, why do we divide it by n minus 2 instead of n? We see that we have estimated beta naught hat. Actual value of beta naught is not available. Beta 1 hat, actual value of beta 1 is unknown. And when we have calculated ui hat, we have calculated it yi minus beta naught hat minus beta 1 hat xi. Since we have used two estimators here instead of their actual values, so 2 degree of freedom is lost. That is the concept. We divide it by n minus 2. Okay, fine. So far so good. I hope so. R square is 0.05. It means 5% of the variation in test score is explained by class size. Standard error of regression 18.6. It means whatever you are going to predict, there will be plus minus 2 standard errors. 37 points of your guess may be above or below, which is a very large value. So smaller the standard error, better your guess is, more precise your results are. That we have covered. What is OLS estimators? What is sample regression function? How do we estimate beta 1, beta naught? And now we are going to discuss what are the assumptions required for this OLS estimator. This is slightly a different text, and it has discussed these assumptions in a more simple form, and has keep on building up these assumptions rather than listing all these assumptions at one place. So we are going to discuss these three assumptions here. Expected value of u given x. It means x and u are independent. X does not contain any information from which you can predict y. So u is random. If u is not random, it means there is some systematic error in this, and we need to reformulate model. We'll discuss it in multiple linear regression. This implies that beta 1 hat is unbiased. Unbiased means that if we take a large number of samples, each sample will get beta 1 hat, then beta 1 hat, then beta 1 hat, and if we take their average, that will be equal to population mean, that will be equal to beta 1. That's concept of unbiasedness. Unbiasedness concept is basically a statistical concept. It has not much practical utility in economics and observational data, because mostly we have one sample observed. We don't know whether if we'll get one beta 1 hat, whether it's lower biased, upper biased, unbiased, we don't know. X and Y are IID so long as we are not talking about time series data, we are talking about observational cross-sectional data. We'll assume that X and Y are IID, independently, identically distributed. Independence means there is no, that is future, you cannot predict one from the other. If you cannot predict future from the past, it means independence. If you can do that, that's called, and it's time series data. It's really helpful, but in cross-sectional data, usually my blood pressure has nothing to do with your blood pressure. It means that this is independent data. And identically distributed, if we have male and female in class, both in class, then it means you don't have homogeneity. So homoscedastic means identically distributed. Heteroscedasticity means they are not identically distributed. More on this in coming lectures. Large outliers are rare. Usually this assumption is not listed in many of the econometrics textbooks. So the large outliers are rare. If there is an outlier, that will lead to biasness in OLS estimator. We'll discuss in a short while that how does it leads to biasness. Basically it means you should have a finite kurtosis. You should not have very huge value of kurtosis, finite fourth moment. So in this case you have identically distributed data. That is, if class size is 15, 20, 25, you have more or less same distribution, and that blue line passes through average, so it's okay. We'll discuss in chapter 5 that what happens if there is heteroscedasticity. Ideal situation, which is not available in most of the observational data and in economics, that is, you should have randomized controlled trials. If we have a class of size 100, we have 50 students in one class, 50 students in another class, or 33 in one, 33 in another, 34 in another, and we try some strategy of large class size, small class size, or teaching them by one tool, teaching by another tool, teaching by this online mechanism, and then what we see that what does this teaching methodology how does this teaching methodology impact their test score. But usually it's not the case. So what do we have to do? We just observe data, we collect data that how when you have small class size, when you have large class size, so we just observe this. But in randomized controlled trials, if we have this, then the other factors become independent of your explanatory variable. That's the main advantage of randomized controlled trials. But at the moment, that's not our topic. We are dealing with observational data. So second assumption, so if you have this first assumption, then it means u given x is 0. That is, x is not helpful in predicting y. Second assumption I have explained it in detail. Fourth assumption is, third assumption, this is infinity, this is infinity. Third assumption, that is large outliers are unlikely. If there are large outliers, then your OLS estimators will be highly biased. Then you should go for least absolute deviation method. That will also have discussion at some stage. Okay, let's go. If I ask you that fit a line on these black dots, most of you will think, okay, this seems a good line because it passes through these black dots very closely. If we ignore this line, if we ignore this outlier, this seems perfect. Okay, fine, absolutely no issue. But as I mentioned, that what is OLS? OLS basically minimizing sum of squares of residuals. If we fit this line, basically distance between this point and this point is u. This u, and it's a very large value of u, and when we take its square, it becomes a very large value. So in order to minimize sum of squares of residuals, what happens that this point pulls this line towards itself, and it makes the line slightly far away from these points. So the line you will fit in presence of outlier will be this one. Please note down that if there is typographical error or some such type or some error like this, it's okay. Ignore that outlier, make a correction, but otherwise don't omit outliers. Aeroplane journey is safe if we exclude airplane crashes. That's nonsense. Financial investment is very safe if we ignore all financial market clashes. So we cannot ignore outliers. That's another topic for another place. Almost the last point, sampling distribution of the OLS estimators. If yi is equal to beta naught plus beta 1 x1 I plus ui. If ui is normal, y is a linear function of normal. So y is normally distributed. If y is normally distributed, beta 1 hat is a linear function of y. So beta 1 is also normally distributed. So it's okay so long as ui is normally distributed. Even if ui is not normally distributed, we don't have any serious issue. Why do we don't have any serious issue? Because you see, okay, these are the things which you have already well familiar with probability and statistical inference. You see, this is sum. So from central limit theorem, we know that even if original values y or u or these are not normally distributed, the distribution of sum or distribution of means, that is normally distributed. So for large sample, we don't have any issue here. Okay, so you see, this is yi, this is its mean, and yi minus y, subtract second equation from the first, you will have this one, and then we substitute yi minus y bar by here this value, and what do we get? That sum of xi minus x bar and xi minus x bar into ui minus u bar. So this is sum of xi minus x bar square, this is xi minus x bar square, so this will cancel out, and we take this beta 1 on this side equation left hand side, and we are left with this one. So in many textbooks it's written that x are pre-assumed fixed values, which we are not assuming. We are assuming that x are random variables. So if x are random, and then you cannot say then you cannot take x outside expectation and you just apply expectation on ui, and you say expected value of ui is 0. Expected value of ui equal to 0 means x is fixed. What we have assumed that expected value of ui given x equal to 0. So you have to do little mathematics. It's given in appendix chapter 4, and you will do little algebra, and you will come up with this result, beta 1 hat is equal to this one. Now you have to apply expectation on it. When you apply expectation on it, you have law of iterative expectations, and this line is basically given that. This line is given that. This line is given that. So we say this is in square bracket, given that x1, x2, and from this appendix you will see with little algebra that this is equal to 0. So expected value of u given x equal to 0 means expected value of beta 1 hat minus beta 1 equal to 0, which means this will be equal to beta 1, which means OLS estimator will be unbiased one. But what is unbiasedness? That if you take so many samples, you take a large number of samples, every time you will have a beta 1 hat, and then when you take its average, the average will be almost equal to beta 1. So practically this unbiasedness is not of much utility for us. Okay, fine. Final, just we are going to talk about variance, and one very important point, that why sufficient variation in x is required. So please be with me, just 5-6 more slides. So if you do this calculation, this little algebra, you write this whole new I and beta 1 hat equal to this one, and now you apply variance. So what will be variance of beta 1 hat? This will be equal to variance of this one, and this will be equal to variance of nu divided by n sigma square n. So variance of this one divided by sigma 4x. Sigma 4x means finite fourth moment. If it's a very large value, we'll have a trouble. If it's a very small value, again we'll have a trouble. How? I'll explain in a short while. So what is sampling distribution of OLS estimator? As I explained, that sampling distribution of OLS estimator is normally distributed for large sample and for small sample. If ui is normally distributed, then yi is linear function of ui, and beta 1 hat is a linear function of yi. So any linear transformation of a normal random variable is normal. So beta 1 hat will be normally distributed with mean beta 1 and standard error or variance this one. Why do we need this distribution? For statistical inference. When do we say that beta 1 hat plus 1.96 standard error of beta 1? So why do we say that we are 95% confidence interval? Because we assume that beta 1 hat is normally distributed. Fine. Now I am going to make very important point. The larger the variance of x, the smaller the variance of beta 1 hat. So if you increase spread in x, means if x has sufficient variation, if you are taking people with having large variation in their heights, it's better to it's easy to predict the weight. I am going to make it further clear from this point. You see, okay, and this graph I have already uploaded R codes to make this graph. So please watch those and replicate that. If I ask you that fit a line from these blue points. If I ask you fit a line from these points. Okay, please think. Fine. If I ask you to fit a line from this whole data, you all more or less like this way. So it means when you have small variation in x, there is little to predict y, because you are trying to predict y from predictor. If predictor predictor does not have much variation in it, it's difficult to predict y. If you have all people in your sample having income, let's say $50,000 per year, or $51,000, or $52,000, $55,000, it's very difficult to predict their consumption behavior, as compared to if you have people in your sample who have $30,000 to $80,000 per annum income. So smaller the variation in X, more difficult it is to predict Y. So large variation in X is always desirable. I give another example. If we are trying to predict money demand or output response from interest rate, and in interest rate you have just interest rate somewhere between 4.5 and 5.5, you have never ever observed what will happen if interest rate goes to 9% or interest rate goes to 2%. You can't comment a lot that if we vary interest rate by a large by this magnitude, this will happen, because you have always observed more or less interest rate equal to 5%. So please, larger the variation in X, better the prediction in Y. So that's what is I have explained that beta 1 hat is unbiased estimator. Its variance is directly inversely proportional to n. Larger the n, smaller the variance, and greater the variation in X, smaller the standard error of beta 1, and it's normally distributed by central limit theorem. And that's what we have discussed so far. How to do this testing of hypothesis statistical inference by using California school data, that will be explained in chapter 5. And we see there are so many other variables which may influence your test score beside your class size, that will be explained in chapter 6, multiple linear regression. Thank you for watching. Take care.